Let's, okay, it's off. Won't make any sound anymore. No, no, that was, okay. Hello, everyone. So today we'll be starting the school with some, like, so with the lectures on resurgence and applications in theoretical and mathematical physics. So first, I just wanted to say a few words of many of the applications that came. So resurgence has has had a lot of applications even beyond theoretical physics, of course, meaning since the since pretty much uh, the so it was found that some of the series, when you try to particular series, that in mathematics, that the series could be divergent, and how to actually make sense of this, there's been a lot of different meaning divergent series have shown up in a lot of different problems. Of course, what we're interested here is the cases where we've seen it in theoretical physics and more generally in mathematical physics. For example, meaning directly related to this, to the school, to the training school and to the program, of course, we've seen cases of black holes, conformal blocks. You know, I think that Giulio is going to be talking more about this, cyber-Witten potentials. There's all these relations, and there's meaning there's the of quasi-normal modes of black holes are directly related to all these non-perturbative exact exact properties. Also, of course, modularity more recently, quantum modularity in Q series. Again, resurgence has shown its tentacles there. You should see, just to mention that resurgence in a whole is a method to understand, is a mathematical method of understanding analytic continuation in a situation where you do not have a finite radius of convergence, where you want to analytically continue your function. It's when you have a divergent series, zero radius of convergence, but you still want to understand the behavior of your function. Other things, so of course, correlation functions in topological strings, matrix models, integral field theories. So all of these have very often, you study them perturbatively, meaning you study some observable perturbatively in your coupling constant, Rn, for example, and meaning you get a zero radius of convergence, a series of zero radius of convergence. Why is this series have a zero radius of convergence? What is behind the fact that we're getting these divergences? And this is the interesting thing that resurgence, the information that resurgence gives you. Other examples, well, meaning that I work on, for example, relativistic hydrodynamics, strongly coupled field theories, and the use of fluid gravity correspondence to actually study, again, black holes, go figure, on the gravity side. Again, so all these things, so you're talking about now what observable energy densities, for example, in your energy momentum tensor. In more generally mathematical physics, hydrodynamics, some toy models used in hydrodynamics, integrable models such as the KDV hierarchy, meaning there's a lot of work being done on this. Initial value problems, boundary value problems. Again, going back to black holes, quasi-normal modes are typically boundary value problems. But boundary value problems more generally in mathematical physics have been analyzed. Meaning, okay, we can build up even more, and you can go, okay, pure nonlinear ODEs, PDEs. Yet again, if you're trying to study a particular problem, you're trying to analyze a solution, but you can only do so locally, perturbatively, but still you want to take out information out of it. So this is where it's coming from. Oh, and of course, I think the last set of lectures of this week is going to be amplitudes. And again, you have a lot of links from resurgence and scattering amplitude in string theory in particular. So this is just so that I can get comfortable with the fact that I'm being recorded and just a general picture of what's going to happen. But the idea is like, okay, you're trying to study some observable, right? You're trying to analyze it. You have a differential equation. You have an integral to solve. You often, if anyone has some experience in integrability, you have an implicit object that say, oh, this solves it completely. But imagine that you were interested in some way to compare it to experiments. An implicit solution is not enough. You need to find an actual value. And to actually get the actual value then becomes a problem. So in many of these things, if you want to actually calculate something, and I'm not even talking about the actual analytic properties, because that's meaning sometimes you can also use the implicit integral or the ODE to find some analytic properties, but can you do it more explicitly as well? So the point is that often, okay, you say, I know I'm in the weak coupling regime, let me expand my observable in weak coupling. Let me try and analyze what I have, because that's the only, that's what I can do. So that's the so that's what I can do. Meaning this is often what you have, and what you obtain is expansions that are often divergent. So you get very often, like, you calculate the first few terms and they seem to be very accurate, and you think, oh, let me try and put a lot of effort and calculate more terms, and you start adding more and more terms of your perturbative expansion, and they start getting much worse, and you think, okay, something is wrong, that this expansion doesn't have a finite radius of convergence. So what's behind, meaning, is this a problem? No, because behind this asymptotic expansion, behind this divergent behavior, you actually have information. There's information there that you can get to that actually is non-perturbative. So you're doing a perturbation theory. You're calculating, like, whatever your favorite method of doing perturbation theory, depends on the problem. You're calculating a series, but behind the fact that it's divergent, you're actually getting information. So if you can retrieve that information, you have non-perturbative behavior. What type of non-perturbative behavior am I talking about? Think in quantum mechanics or quantum field theories. You think of instantons, exponentially small terms that meaning can't be captured ever by perturbation theory, because they're, if you expand an exponentially small term in perturbatively, you get 0 to all orders. So they do have information, and somehow we need to include not just our perturbation theory, but our non-perturbative results. We need to include that all in order to actually get a meaningful result. And moreover, if we wanted to analyze the properties analytically, we would also need to have not the local behavior, but we need to be able to analytically continue beyond that. So how do we do this? The question then is, how do we retrieve information from just this divergent asymptotic series? So I'm telling you that there is information there, but how do we get it? So a few things that I would like to mention before I actually start writing things is that, so asymptotic series, meaning if, for example, I'm saying weak coupling, but sometimes in string theory, meaning you can go to weak coupling, you can go to strong coupling. One of them will be convergent. Why don't I start on the convergence side and calculate, a convergent series, finite radius of convergence, everything. So asymptotic series can be much more effective at calculating, even though they are divergent, they can be much more effective at approximating a function. Also, again, as I mentioned, if I analyze these divergent series, I can get non-perturbative behavior. I can put them all together, which in something I'll call a trans series, but I can put it all together and get something like a completion of my observable, of my correlation function, for example. And finally, this is all still perturbative. This is all still series. The series are divergent. How do I take a number out of it? There's ways of summing it. And what I mean by summing it is that actually you can sum these trans series, these series, such way that you can get the analytic behavior of your result, of your observable. So just so this is more or less what I'll try to do, let's hope. So I will start with the resurgence and what is Stokes phenomenon. I will go then a little bit more onto the mathematical aspects of it with Descartes' resurgence. And finally, I will end with this idea of that you can actually take information, analytic information out of these series, these divergent series and these trans series. So I will now try and introduce the idea of Stokes phenomenon. So asymptotics, or an asymptotic series, has been introduced a long time ago by Poincaré in 1800s, such that if you have a function, y of z, and we're taking z, assuming z belongs to some particular sector in the complex plane, then a series is asymptotic, meaning the function is asymptotic to some series. And this series can be, so AR, and I'm sorry, my handwriting tends to devolve, so whenever you find it very difficult, tell me to pay attention, then I try to go back to. So I'm talking about now, I'm assuming now Z might being something large. So S is just some particular sector in the complex plane. What do I mean by this asymptotic behavior? Meaning you must have seen this before. It means that for any truncation n, I can calculate the remainder. So I can calculate a remainder, Rn, which is definition, it's like the function minus some n equals 0 to n minus 1 ARZ minus R. And this will be of order z to the minus n, which is less than equal than some number modulus z to the minus n. So, meaning this is true whether the series is is divergent, convergent, it doesn't matter. I can define a remainder always. But the thing is that if a series actually had an exponentially small term as well, then you'd get the same asymptotics. Assume that I have y of z plus e to the minus z. This is so it's 0, like I said. The exponential is 0 to all orders. So, so this plus an exponential is the same as y of z. But we'll see, actually with Stokes phenomena, that it's there'll be regions, like I said, this is a region, a particular region in the complex plane, but there will be different regions where even though you have that exponential can become extremely large and actually dominate your result. So then, then it's quite important to just not to go beyond this understanding of asymptotics and incorporate any exponential terms that we thought were so small that we could ignore them in terms of the asymptotic behavior, because they actually can dominate your system in different sectors in the complex plane. So, and now we go back to the prototype example always of resurgence, which is the Airy function. So it's one of the first problems with Stokes phenomenon. This was by Airy, in that he was very interested in understanding what's called the supernumerary fringes of rainbows. And let me just take you. So the supernumerary fringes of the rainbows are actually, it's not the double rainbows that you see sometimes above the main rainbow. It's these, mostly, they're purple and, yeah, green and purple, basically, just below the rainbow. Why did he care about this? Because this actually was something, there was a fringing effect also in optical lenses, and he was an astronomer. So he was very interested in trying to understand that behavior in lenses. So, meaning this can be understood using the theory of rays, and basically Airy used the theory of rays to to write a mathematical formula known as the Airy function, for which the intensity of light of the primary, secondary rainbows, and also the fringes can be obtained. So if you analyze the axis perpendicular, so perpendicular to the rainbow, the intensity of light is given by the square, so y square of x, where y of x is called the Airy function, ai of x. And it obeys d2y dx2 minus xy equals to 0. And of course, initial data is y of 0 equals 1 over 3 2/3 y prime of 0 equals minus 1 over 3 1/3 gamma of 1/3. So this is the initial data. And this is how the function looks like, if you look. So basically, the top thing is the main bow, and all the other maxima minima are the supernumerary fringes. So he's interested in finding the positions of these maxima minima. What can we do? Well, we have the differential equation. We can plug in a series at the origin and see how far we can go. So it's convergent. But as usual with Taylor series that are convergent, the series is too slow. Sorry, just a second. So the red is again the original series. If I add 4 terms, that's the blue line, and you can see that I almost get the first rainbow. 4 terms at the origin of an expansion. 12 terms, it's the, sorry, you might not be able to see, it's this one that does get the first rainbow and then escapes. So it gets the first rainbow, the main rainbow, but doesn't quite get the next minima. 20 terms, it's the green one. First rainbow, second minima. 40 terms is the next one. Gets the first one, second one, third one, almost predicts this one and then flies off. 40 terms. You have to think, we're talking about what? Mid-1800s? This is a lot of work without a computer. Here it's very easy, but it's a lot of work without a computer. I mean, it's not really doable. You can't, okay, you already predicted some things, but this is me with 40 terms in Mathematica doing in no time. I'm just saying that this wouldn't be doable. Like, again, this is Mathematica doing for us as many terms as you want, sure, but it's very slow. So then comes George Stokes around 1850, and he came up with the uses of divergence series for approximation. So where does this divergence series come up here? Okay, instead of around the origin, let's expand around infinity. It seems like very far away, right? But let's try it. So this is, I guess, G. Stokes, George G. Stokes. So what we do is, like, we take modulus of x goes to infinity, and then you can, I will write the actual expansions, but I just wanted to say, because we're doing x real, so what happens? Actually, something strange happens. So for x positive, you get e to the minus 2/3, x to the 3/2, and now I just broke this, divided by 2 square root of pi. This is x to the 1/4. And this is for x greater than 0. For x less than 0, I get sine of 2/3 minus x to the 3/2. And now I have a question. How many exponentials do you see in the expansion x very large positive? I'm not saying that it's a difficult question. Come on. 1. Great. Very obvious. How many exponentials do you have on the second negative exponential? Sorry, negative x. 2. So typically, if you're talking about a series of finite radius of convergence, you can't turn one exponential into 2. So you have a different number of exponentials. This is, again, modulus of x goes to infinity. You have a different number of exponentials, yes, for x greater than 0 and x less than 0. So basically, what I'm saying is that this series, obviously, they can't be valid. This is just the first term, by the way. First term. These have corrections. This would come with 1 plus x to the minus 3/2. Is that correct? Yes. So x greater than 0 plus some number x. I will write these things down. But so it comes with extra terms. So does this. So it's not that I'm just taking the first term. So in the same way as we were doing the Taylor series and we calculated 40 terms, this is only the first term in this series. So somehow this asymptotic, this series, the function is asymptotic to this in a sector close to the positive real axis. I don't know how long, how wide this sector can be in the complex plane. And here, in the negative real axis, again, the same thing, right? But I can't have both of them be true all throughout the complex plane. Somewhere, we have to swap one to the other. So now the question is, how accurate is this? So this is the result of one term of the series. And one term of the series basically gives you, in the negative real axis, the supernumerary fringes, plus pretty much the first rainbow. And in the positive real axis, the exponentially decaying behavior that you see. Of course, meaning you're doing at x infinity, at x equals 0, it's this is not enough. But the point being is, really, we did it infinity, and we can go extremely close to 0 just with one term. We had 40 before. If we calculated 40, well, we'll see, it's divergent, so it's an issue. But still, the point being that I wanted to show that, indeed, this is extremely, meaning asymptotic series can be extremely accurate. Yes. Sorry, and the purple, blue, it should be blue, it looks purple, it doesn't matter. The purple is the positive real axis one. Yeah. But we know that you can't take one to the other, because somewhere, in the negative real axis, one of them is valid, in the positive real axis, the other one is valid, so we can't. At the moment, we don't know how to swap one from the other. And this is actually, that's what Stokes phenomena is. It tells you how to go, how one exponential turns into two, in this case. So, and that is, that's very easy. No, the series around 0, no matter whether you change variables, it's convergent. The series at infinity, meaning you could write x 1 over y, meaning y no, because y is the function, 1 over z, and z 0, but you're still doing at the infinity of the Airy function. So the idea is that in one of the regimes, it's asymptotic, as we're going to see. In the other one, there's a finite convergence. Taylor series, they're convergent, they're slowly converging. These, meaning there's I'm hiding a little bit some things, which is the fact that the Airy function, unlike many problems that we have, especially nonlinear problems, here there's two exponentials always, right? And I'm hiding that slightly. Because usually, especially in nonlinear problems, you have a true perturbative series, meaning no exponentials associated with it. Just to mention. Here there's always one exponential, but in any case. So now we'll go slightly more to the point. And so we have the Airy equation, the differential equation, and what we do is a formal, and I'll explain why it's formal, large X expansion. So y of x, sorry, just 1 second. This is just the variable that shows up in the exponential. This just makes some of the equations look smaller, okay? So it's just a redefinition. And what I have is that this is minus this psi of x, so, or zeta, sorry, zeta of x. So let me just, here it's the only place that I use the x to the fourth just because it's, but this is the same, meaning it's the same function. And I have, so I have two solutions, y1 sorry, that's not what I wanted. uh, so why do I have two solutions? This is a second order linear ODE. There will always be two solutions. This is an infinity, by the way. Where are they valid? Well, this is valid when argument of x everywhere except in the negative real axis. And this one is when argument of x so these series, and I haven't written what Cn is. You can see that the series in themselves, they have actually the same coefficient, but this one comes with a -1 to the n. So they have two exponentials, two possible solutions. Again, second order linear ODE. This is for large x. And so the y1 at x positive, this is basically the Airy, what I've written there as the first term is just at that negative exponential. But of course, each one of these has its own exponential. So somehow, in the negative real axis, I'm looking for something that is that has both of these solutions. So these are, why are these formal series expansions? Because they're divergent. Cn, you can calculate Cn via recursion relations. Basically, you put an ansatz that has an exponential, a power of x, and you can directly calculate the Cn by recursion relations. It gives you Cn plus 1 is going to be Cn and something. And so this is and by the way, so again, not looking at the physics, the most general solution of this is going to be a combination of them, of course. So what you have is y of x is equal to some sigma 1 y1 of x plus sigma 2 y2 of x. So this is the first example of a trans series. What does it mean, a trans series? But it's an extremely simple one. What's a trans series? A trans series just means that you have a formal series in your power series in your variable, but also you have a series in other monomials, which you're assuming that are small. What is the other monomial? So the two of them are exponential of minus xi and xi to minus 1. Of course, in this case, the series in the exponential is just, well, if you put one of the exponentials outside, the series in the just two terms. So in general, you can have an infinite number of these exponentials as well. But so this would be a trans series in the sense that it's not just a power series in my large or small term, which is x, sorry, 1 over x, but also these exponentially small terms, which are exponential of minus xi. So I just wanted just to give you a hint of that. So what do they look like? For example, if you look at energies in quantum mechanics, you have things like this. And this is just as a, sorry. So this is a type of Tron series you could find. Power series, exponentially small terms. A is the instant on action. You might think of that. But there's also logarithms showing up in finite number, meaning here usually infinity has a finite number for each n. But so a Tron series is just a formal series in not just your small parameter, but also other monomials can show up. So I just should check the time. Yeah. So just to mention that when I said earlier on that that we know that somehow our series Divergent has information about non-perturbative phenomena like instantons about this. So it has information about this A, and in order to actually understand the full observable, the full amplitude, the full correlation function, whichever energy density, what you need is to find a completion of that observable. That's what the Tron series is your completion, non-perturbative completion of your perturbative series that you're calculating. So I just wanted now to mention that. So here, look at the original asymptotic expansion that I have. At argument of x equals to 0, so if I have argument of x equals to 0, what I have is what? Sigma 1. So sigma 1 equals to 1, sigma 2 equals to 0. Right? That's my solution. But when argument of x equals to, and now I'm pi, yes, which is the negative real axis. I have sigma 1 equals to 1, but sigma 2 is going to be, and I leave that as a homework. You can expand that sign, compared with these two exponentials with the square roots, the square root of pi already here. You can see that the sigma 2 is going to be I. So somehow, between 0 and pi, my solution changed. And instead of having the same sigmas, I have one that swapped from 0 to I. So in order to understand this, we need to understand the whole complex plane. And now I'm going to talk a moment about optimal truncation, which is one of the ways that you can see when adding the second exponential actually makes no difference. Now, in fact, what we're going to see is now we're going to analyze the Airy function. Instead of being just in the real axis, we need to analyze it in the full complex plane. And what we're going to see is that the error, remember that when you do, there's going to be an optimal truncation, so a point that we can truncate the series where we get the minimum error to the value of the series. And what we're going to see is that there's going to be at a point where that error is exactly of the same order as the second exponential. And basically adding that second exponential is within the error, and you just turn it on and you continue it and you get both of your exponentials. This is one of the things when we're going to, just after this, seeing this from the point of view of saddle point analysis, which also makes it slightly more clear. So I'm going to delete the remainder, but I'm going to go back to the remainder. So optimal truncation. So I know in the positive real axis that I start with just the solution y1. So I have y1 equals e to the minus that psi. And now I'm saying that I'm truncating it at n minus 1 terms. So I have Cn minus 1 to the n over psi to the n plus the remainder. So, and I want also to compare it with let me call it dr because it's different, plus rn c from convergent. So, and what I wanted to show you is that at x equals 4, let's just put it x equals 4, this is the type of thing that you get for the remainder. So this is just as a comparison. But so at x equals 4, adding this is the number of terms that you're truncating at, right? And basically the error to your solution slightly increases and then starts to steadily decrease. This is the order of the error. This is log 10 of the remainder, so log base 10. So, and now you can look at the remainder of the asymptotic series, so this one. And that one is here, where you can see that actually that the error decreases very rapidly, right? Because this is a log-based plot, reaches its minimum, and then increases. So from the plot you can see, and this is always true, from the plot you can see that there's a clear point where you should, truncate your series where you get the best results. So that's optimal truncation. So basically what I want is truncation to minimize the error. So what I want is, if I have y1 is equal to sum in an, what is an? An is basically the whole thing, right? So an is e to the minus xi over 2 square root of pi x to the quarter cn minus 1 to the n divided by xi n. So it's the whole thing. And what do I want? I want to know I want to make sure coefficients are still decreasing. This is the same as writing, if you look, meaning, because these are gamma functions, you can easily write this, right? N minus 1 over 6, n minus 5 over 6, divided by 2n modulus of psi. And I'm talking about, I'm assuming that n is large. So I have, this is so this is my optimal truncation. So n optimal is the floor function, because I want to know the last one that where this is true. So optimal truncation, you can see it here. Optimal truncation depends on the value of psi. It's not a value always the same. It varies with psi. So this is optimal truncation. And by the way, this 2, why 2 here? Because that 2 is related to the distance between the two exponentials. In this case, we have two exponentials, plus psi minus psi. So the distance between the two exponentials is 2 psi. So if I had put one of the exponentials, if I put in evidence one of the exponentials, one term would be perturbative and the other one would come with 2 psi. So optimal truncation actually is pretty much what shows up here is the value in the exponential of the difference between the perturbative series and the first exponential in this case. So in this case, it's 2 psi because we have two exponentials. So this is the optimal truncation. It's the value where we should stop. Now, what is the value of the error? That's the one thing we want to analyze. So I know that this guarantees for me the minimum error possible. But can I evaluate this error? And I can. Basically, you can use Stirling approximation. And I am not going to do this because every time I do this, even last night I was doing it and I got one factor wrong. But in any case, what we really care about is the value of the exponential. And that one is quite easy to see. That if you use the Stirling approximation, the modulus of an for n optimal is going to be equals to, and there'll be a factor over modulus of x, and then you get minus psi minus 2 modulus of psi. So obviously, the least term is exponentially so we're stopping. So this is basically for n equals n optimal, right? So this is the last term that we're adding or that we're ignoring. The first term that we're ignoring, the last term we're adding. It's exponentially small and is smaller than the second exponential. The second exponential at the moment, well, depends on where we are in the complex plane, like I said. So if you look at the two solutions, one of the exponentials comes with a minus psi, the other one comes with a psi. Psi is very large, obviously. I'm talking about something very small. But is there somewhere in the complex plane where these two exponentials actually become of the same order? That's the question. So I started, now this is the complex plane of psi. I started here for psi very large, right? X very large. And I'm wondering how I can go here for x negative. So this is, sorry, this is not psi, this is x. I want to know where, so is there somewhere in that plane where actually the error that I just calculated for the AN is actually of the same order as the second exponential. So if argument of x equals 2/3 of pi, 2 pi over 3, so 1 there, somewhere. Sorry, it's almost pi, sorry. Assume that that's 2 pi over 3. This means that argument of psi is equal to pi. And that means that e to the psi, which is the one that shows up in y2, is equal to e to the minus modulus of psi. Now, the error, so this is the exponential in y2. So the second solution. So now the e to the minus psi minus 2 modulus of psi is equal to e to the minus modulus of psi. Because minus psi is minus minus modulus of psi, so it's plus, minus 2 modulus gives you that. And this is the error of optimal truncation. Of y1. So where is it in the complex plane where the two exponentials actually become of the same order, such that one is actually compensating the error of the other? And it's exactly here. So what I'm going to claim is that crossing that line is exactly where I need to take that parameter sigma to jump. Because adding the second exponential is not changing the error of my analysis. Why? Because they're actually, again, I'm adding something that is exactly of the order of the error of the other, of the optimal truncation. So that means that, let's do colors. Up to here, I have, oops, y1. And here, I have y1 plus I y2. And now, meaning I haven't explained why I, meaning it seems that, okay, I could say that I know for physical reasons that it has to be I. But there's actually ways of calculating this I. We haven't gone to here. And this is Stokes' phenomenon. It's the point in the complex plane where I know that I pick up a second solution, which I know will be essential to describe the analytic behavior of my solution if I continue further. So I know that in the negative real axis, I need both solutions. I know in the positive real axis, I only have one. Where in the complex plane can I pick up the other one? At the Stokes lines, where basically the second exponential is as exponentially suppressed as possible and of the same order as the error of my first solution. So that's okay. This is Stokes line. Again, all these things, I will make this more mathematically precise later on. I'm just trying. all the terms, the terms after that start growing. So you're stopping to have a solution that is actually converging. So you can do an analysis of the remainder and show that it's decreasing up to that point. In fact, I guess that the moment I showed you an ad hoc plot, quite clear that that's the point and how to calculate it. But you can actually do an analysis of you know, the derivative of the remainder in some way, and show that in fact it's decreasing up to that point. No, no, no. It only gets worse. So what is the remainder of the sum of these two solutions with two opposite exponentials? Now you're talking about, like, the definition of the remainder is a remainder of a truncation of a series. In fact, there's ways of defining a remainder, meaning you can add exponentials and define new, this is level 2 hyperasymptotics, or level 1. Oh God, I can't remember where it starts. Where basically what you find is that to actually decrease the error when you add the second exponential, you need to add about twice the number of terms of the first exponential, add optimal terms of the second exponential, and then the error goes down again before it starts increasing. So there are ways of constructing this exponential by exponential. There's also ways of not doing the whole optimal truncation, which we will talk about afterwards. But in any case, I guess that the reason why I'm not going directly to Borel plane, Borel transforms, and everything is just that for a lot of your first zeroth order analysis, optimal truncation is all you need. And you can learn a lot by doing very simple calculations like that. So you don't need to go beyond that. Of course, if you really want to analyze and sum, that's, again, hyperasymptotics works very well, but adding more and more exponentials becomes more and more complicated. But there are ways of defining the remainder, indeed, and to decrease the error. And you can show that the error does decrease by adding the second exponential. It's not with the same number of terms, in fact. So I wanted to now, so I was saying, this is Stokes' line. I just want to also define this line. This is an anti-Stokes line. What's an anti-Stokes line? It's the line where if you did pick up the two solutions, they become exactly of the same order. So at that line, if you had forgotten one of the exponentials, you'd get a completely wrong result. You never get zeros, because it's the fact that you have these two exponentials that you get sines and cosines that will give you the zeros. If you only had one exponential, you would never get the zeros. So the anti-Stokes line is the line where basically the exponentials are all of the same order, of order 1. So is this universal? Does this always happen, this type of behavior? Does the Stokes phenomenon and the behavior of the series as being factorially divergent, like these CNs that we're finding, is this universal? And it is. So this goes back to mid-1900s by Dingle, where he did see that basically the late terms of asymptotic series have always a universal behavior. So the perturbative series, assume perturbative series as the series of y1, apart from this exponential. Like I said, every function has two exponentials. A lot of our problems have an honest perturbative series and then exponential corrections. So the divergence of perturbative series and the Stokes phenomenon are basically intimately linked. So the fact that these CNs are divergent and the fact that there's a Stokes line where you pick up the second solution, which is also divergent. There's a very clear link between them. And and this can be seen by what's called the large order behavior. What do I talk about large order? Large order means I have a series here, like n equals 0 to infinity. The large orders are the CNs when n is large. So that's the large order behavior. So I just said, if I include extra terms, they get worse. But the fact that there's this factorial growth that makes that sum worse is where the information is. So basically, and let me now, I'll keep that. And I delete this. So the diverging late times, so we wrote that generally y of z, or let's write x. Y of x goes as sum n greater or equal than 0, sum an x to the minus n. I'm talking about x goes to infinity again. And the late times behave as x minus n an goes as some number gamma of n plus nu divided by x a n plus nu. So what am I saying here? I'm saying that if I analyze these terms when n is large, so I'm taking n very large, and the behavior when n is large goes as a factorial growth divided by a subleading exponential growth. And this behavior is universal. It's always there. There's always that constant, and that constant actually has meaning, by the way. So the coefficients always behave as factorial over power. And yeah, the optimal truncation is such that, so if you take optimal truncation, you have that the remainder of n optimal is of order exponential of minus a modulus of x divided by something like that, about. So it's exponentially small if you truncate it correctly. So, but this is the universal behavior, but my point is that going beyond this universal behavior actually gets you information. So what if I analyzed, look at the coefficients, by the way, the coefficient Cn, I don't know if I've deleted them. Oops, no, they're here. The coefficient Cn, if you take n large, this is a factorial growth, this is a factorial growth, this is a factorial growth. So you get one factorial growth at the end when n is large. And actually, basically, what you have is that if I went and analyzed this, I got the ANs, so they have this thing divided by a to the n plus nu, and now I have 1 plus d1 over n plus d2 over n squared. And I can analyze this large n behavior if I calculate the coefficients. I can analyze the behavior. What is the information in d1 and d2? I don't know if you've seen anything about resurgence. And this is when we start talking about resurgence properly. So here, the coefficients an, again, I I should have been more careful because Z, X, I keep on changing variables. This should be psi. Just to kind of compare with the, sorry, it doesn't matter. This is just it's just to kind of compare with what was written there. Actually, no. See, I know that I shouldn't do this because I actually wanted to keep the A because the A is the instant on action. And when I define psi, the instant on action is 1. So let's keep X. X is X to the 3 halves there, so sorry about the bad notation. The point being is that think of these ANs as the factorial growth of these CNs. There's a factorial growth for n large, and then there's an A to the n plus a half. In this case, is going to be 1 because I defined it with size. But these D1s basically will give you the coefficients. So sorry, let me go back here. It seems a bit obvious because the CNs show up here and the CNs show up here. So it looks like the same, meaning the fact that we have the same CNs, that's what will always show up. But my point is that if you're doing an analysis of an asymptotic series, it doesn't matter where it comes from, and you do this, this behavior at large n, so the large order behavior, the coefficients D1, D2, D3 are going to be the coefficients of your first exponential in your trans series. So in the factorial growth, if you study beyond the factorial growth of these ANs, the coefficients that show up here are exactly the coefficients of the other solution. So imagine that you didn't know the other solution at all. You didn't have access to it. You can have access to it because that's what the information is encoded in that factorial growth. So this can be done in many ways, but say the easiest way is using Mathematica. So this is the coefficients here. This is the coefficients of the y1. This is the coefficients of the y2. Obviously, they just vary by the -1 to the n. There's no difference in them because we know that the coefficients of the y1 are cn -1 to the n. The coefficients of the y2 are just cn. That's easy. But what I want to do is analyze the series of the coefficients of the y1. So I'm dividing by the factorial growth, just because so what I want to analyze it, so let me just write n goes to infinity. And now what I'm doing is, let me do gamma n divided by n plus mu. If I divide this, I should get directly this for large n. That's what I'm doing. So if I do that, you can see that I get coefficients 1, minus 5 over 36, 25 over 2592, etc. And here we still haven't, sorry. So now I've written this in a slightly different way, and I'll explain. We still haven't gotten there, but basically, now I can delete this. It doesn't make a difference. So what is written there, I am saying that what I should get there, instead of D1, D2, D3, etc., what I will be getting there, and again, this can be derived and will be derived, but at the moment I just wanted to show you that there is such a thing. I get 1, sorry, -4. starting to need glasses. So if I'm not mistaken, this is exactly. So if you look here, I should get, so A is the same A as should be showing up here. So if I wrote this series as 1A C1 divided n minus 1, A squared C2 divided n minus 1 and minus 2, then C3 plus A cubed C3 n minus 1 and minus 2 and minus 3, and then on. And of course, now I expand in n. And what I get is exactly the same series as I'm getting here. So basically, this series that I have here is the exact same series as I have here, where the C, now these C's, A is minus 4/3, because I'll explain. It's minus 4/3 in the variable x. Again, I think that I need to analyze this. I just wanted to show a brief moment of what we expect. So the C's and these CNs are the coefficients of the, I deleted, of course, now, are the coefficients of Y2. So CNs are the coefficients of Y2, so, and they show up exactly in this form with the higher n's. And then, of course, when you take large n, the first one is AC1, but the second one will have an AC1 and an A squared C2 mixed in, because you're taking 1 over n squared is going to mix the two of them. How can I get these expressions? Meaning these expressions can be, again, derived exactly. So we will get these expressions. These are the large order relations. But what I wanted to say is that if I analyze the coefficients of one of my series beyond the factorial growth, what I get here in the D1, D2, D3 are the coefficients of the other exponential. Again, one thing that I wanted to say is don't be hung up on the fact that they're both CNs, because this is particularly true for the Airy function. But this is true in general. So the coefficients of the other series multiplied by the term that shows up in the exponential, which is the A. So I guess that the one question that I have is, how would you determine, meaning I said that I could do this large N analysis. How do I determine the mu and the A in this case, if I have the ANs? So imagine that I have the ANs. I'm telling you that if I calculated these terms, I could calculate this D1, D2, which gives me access to the next series. But I haven't told you how to calculate the mu and the A. This is just a numerical kind of exercise. If you calculate AN plus 1 divided by AN, it will give you directly that, by the way. So if I do AN plus 1 divided by AN, that gives me kappa disappears, gamma of n plus mu, n plus mu divided by gamma. This is gamma n plus mu plus 1, n plus mu. And then I get multiplied by A. So the gammas divide, n plus mu divided by A. Of course, I have the whole series here, 1 plus d1 over n plus 1 plus etc. And here the series as well. But the thing is that to first order, this gives me n over A. the next order will give me mu over A, and then you get the extra ones. So if you're doing if you're analyzing these ANs for large N, especially if you divide here by N, you get 1 over A plus the next one is going to be mu over A, and you actually get access to the A and the mu, and you can calculate them. This can be done precisely. Of course, in this particular case, you can even do it more because you can use Stirling approximation in the gamma functions and calculate these exactly. But I'm saying in general, even if you didn't know, you could calculate these by just even plotting the results for the mu and the A. So that's a very good question. I honestly think it depends on the observable you're calculating. So the mu is directly related to, so when you have a perturbative series, so when you have a perturbative series, you have y goes as, I don't know, an g to the n plus e to the minus a over g, so a small coupling. And then you have also another series, bn g to the n, like around an instanton sector. But this series might not start at order g to the 0. It has a g to the mu. This, take this with a grain of salt because I never remember if it's mu minus mu, mu plus 1, mu, meaning, but again, it's and this actually can have physical meaning in the observable as well. But it does depend on what, if you're studying an energy density, if you're studying a correlation function, if you're studying something else. I mean, again, resurgence per se is just you're just analyzing the actual divergent series, but the meaning can depend on the observable. Yep, exactly. In fact, even more than that, if this one didn't start at leading at g to the 0 or something, then it basically signifies the difference between the starting points of those two. But indeed, that's what it means. That's mathematically, that's what it means. But I just wanted to say that this, what I just told you, and this is why I wanted to show before I even derived it, this is telling us that the instanton sector, or the first exponential, or in the case of the Airy function, the other exponential, resurges in the large order behavior of the first one. So y2, the information of y2 resurges the large order behavior of y1, and thus resurgence. And I think that we're done. Let me just, let me just finish with one small detail. I kind of ignored that kappa, which I can't believe I deleted again, where I said that the y, the ANs went as kappa, gamma of n plus mu divided by a to the n plus mu. And I ignored this kappa. But this kappa has a very important meaning. And I think that with this I'll end, but I just wanted to say for the Airy function, so if I do Cn minus 1 to the n, for example, divided by psi n. So this is the behavior for large n now. Actually goes as gamma of n. You can use Stirling approximation for this, minus a, and now I return to the variable x because I wanted to keep that a here, to the n, I divided by 2 pi I. And there's a reason why I defined this. So a minus 4/3. Why did I write it this way? Remember that I wrote here a minus 4/3. This a that shows up here is the same a here. It's exactly the same a. Gamma of n, so mu is 0. And then I have the kappa is I divided by 2 pi I. So kappa is S divided by 2 pi I. This is called the Stokes constant. It is also in the information of my coefficients. It's there. We can retrieve it. And why does it matter? Had you seen I before? Somewhere? Where had we seen an I showing up that was important? Of the second, exactly. Why does the second, why like, how did the jump across the Stokes lines happen? It added I times the second function. That's the same I. And I think we're done for today. And we can ask questions and everything can be now unrecorded, everything.